So here is question 12 from the 2018 AS paper. You've got a link in OneNote to Maths Made Easy, and although they've got work solutions along with the proper mark scheme, but I thought I'd do 3 of the trickier questions. So this is one of these show that questions where you've got to change this into this. So this is an identity question. And at AS we have 2 identities. We've got sine squared plus cos squared equals 1. And we've got tan is sine over cos. And looking at this, I can't see any sine squareds or cos squareds. So this seems to me to be one where it might involve this. All I can do, in fact, is replace this tan with sine x over cos x. So I'm going to do that. So I'm going to rewrite it. 4 cos theta minus 1 equals 2 sine theta times sine theta over cos theta. And if you're not confident with this, be reassured, you can just say, right, so that's one big fraction. Because that's 2 sine theta over 1 times sine theta over cos theta. Sine theta times sine theta we can write as now, if I look at what I've got to show, no sines involved at all, but the only sign I've got here now is a sine squared, and I know that I can rearrange this to say sine squared is 1 minus cos squared. So I'm going to rewrite that. So it's 2 lots of 1 minus cos squared theta. So I've replaced sine squared with 1 minus cos squared. Now I hate fractions, so I'm going to multiply by cos squared. Don't forget I'm going to multiply both of these things by cos squared. Sorry, I'm multiplying by cos. So that means that that becomes cos squared and that just becomes minus cos. And then I'm also going to I've killed the fraction by multiplying by cos, but I'm going to multiply out the top. And you can sort of feel the proof relief at this point, because if I add 2 cos squared theta and take away 2, as required. Okay, so let's have a look at the second part. Now, this is one of those questions where there's a key word. Hence, it means this isn't a random question. This has got to be in some way related to the previous question. And can you see how it is? What's done is that theta has been replaced with 3x. And that's consistent throughout that statement. Now, we've just been asked to show that this is the same as this. So they're begging us to rewrite this as this, but instead of theta, 3x. So let's do that. So we've got so this can be written as this, 6 cos squared 3x minus cos 3x minus 2 equals 0. Now we're asked to solve it for x between 0 and 90. I've actually got 3x in my statement, so I need to solve it for 3x, which goes as far as 270. And I'm going to do a quick sketch of cos as far as 270. It's there. Now, this is a quadratic in cos, so I'm going to solve this with my calculator. I'm going to solve this as just a quadratic. So A is 6, B is minus 1, C is 2. Minus 2. So my solutions are that x is 2/3 and x is minus 0.5. But that's not x, is it? The variable in this quadratic is 3x. Sorry, is cos 3x. So I know that cos 3x is equal to 2/3, and cos 3x is equal to minus a half. So I'm going to pretend this is just x, and 2/3 is valid and minus a half is valid. So I know I'm looking for 3 solutions for 3x. So I'm going to do shift cos of 2/3 back into normal run matrix mode. So shift cos of 2/3 gives me, right, I'm in a different way of measuring degrees called radians, which we're going to meet soon, so I'm going to change that quickly. There we go. Right, so that is 48.2 degrees. That's the only solution between 0 and 270. And I'm going to do shift cos of minus a half. And that gives me 120, which makes sense. And so that's going to be 120 there. So this one will be 270 minus 1. So that's 90. So that is 30 degrees more than that. So that will be 30 degrees before 270. So that's 240. So my x values are just each of those divided by 3. So that's, sorry, so that is 40, that is 80, and that is whatever that divided by 3 is. I'm sure you can work it out. So this is a classic case where they get you to do something, and then they replace the variable, in this case theta, with a different thing, and you use the thing you've shown to solve it. And again, remember that, you know, even if you weren't able to get that, there's still 4 marks up for grabs in the first part of the question. Okay, let's move on to the second one that I had in mind, and that's question 13. Now, do you remember we looked at 2 sorts of graphs? One where you logged both axes, and one where you only logged the y-axis. And one was an exponential growth, and one was a power graph. So here we've got exponential growth. So do you remember how we go from this to a straight line? We say, okay, v is equal to p q to the t. So our variable here is t. P and q are constants. We log both sides. And then we're using log logs, log to the base 10, so log of I can then use the first log rule to rewrite this as the log of p plus the log of qt, and then I can rewrite that using the third log rule Now, if you look at what we've got here, we're given the equation of the line, we're given it here. So this here is this term. I know they've put the t after the number, and I've got the t before, but that's just because it looks a bit odd after for me. So I know that the log of q is 0.05. And this term here is this term. So I know that the log of p is 4.8. Can you remember how to work out the value of q and the value of p? How do we undo logging? This is log to the base 10, so do you remember we do 10 to the power of? Sorry. So we are then asked, remember this is the equation, exponential growth, we're then asked what are the meaning of these values? You know, you would have worked that out and worked that out and rounded it to 4 significant figures. Well, remember p in an exponential growth equation is your initial value, and Q is the multiplier. Now we're asked with reference to the model, so we've got to put this in context, okay? So we know that P is the value of the painting in 1980, and Q is what the value of the painting is getting multiplied by each year. And then we can rewrite this with our value of P and Q in, and we can just make T equal to 30, because that's 30 years on, and that will give you your answer to that one. Okay, here we go, last one. Starts off relatively straightforwardly, so go on pause and just see if you can rewrite this in the bracket form and tell me what the centre and the radius are. Just pause and have a go at that. So I'm hoping this is a technique that you're sort of familiar with. I've written it differently with the x terms here and the y terms and then the 9, so I've just sort of written this in a different order. And then I've completed the square for that. So that would be x plus 3 squared, which would have the x squared and the minus 6x. Sorry, x minus 3 squared, which would have the x squared minus 6x. It would also have a plus 9, so I have to put a minus 9 there, so that equals that. Similarly, that equals that, and you've got the plus 9 there. So then if I sort of hoover all these numbers together, then you're left with a minus 25, which I then add. So that means the centre, do you remember it's the opposite of this and the opposite of this? So it's 3 minus 5, and the radius is the square root of that. Now, we are now told that the line y equals kx cuts C at 2 distinct points. So what we're being asked to do is we're being asked to solve some simultaneous equations. So we've got one equation, which we can now write in two forms. We've got the bracket form, and we've got this form. So I'm going to use the bracket form as they've asked me to write it in that form. That seems to be a bit of a hint, perhaps. Sorry, there we go. And I've also got this equation here. And this is a problem about solving these simultaneous equations, finding out where they meet, except we're not asked to find out where they meet. We're told that this cuts this twice. So there are two solutions, find the range of values. So hopefully you recognise this is a discriminant problem. So I'm going to solve these simultaneous equations by substituting y here with kx. Okay, so I'm going to use a substitution approach to solve it. And if this is a discriminant question, then I need to get this into the form of a quadratic. So I'm actually going to multiply those brackets out. These ones, I've got to be a bit careful here. So k is a number, so it's like 3x or 4x. So that gives me k squared x squared, that's a tricky one, plus 5kx plus another 5kx plus 25. So that gives me k squared x squared plus 10kx plus 25. Now, let's collect everything together. Remember, I always like to line up my quadratics, so I'm going to do the x squareds first. I've got 1x squared here, and I've got k squared x squared here. So are you all right with me writing it like this? One x squared, k squared, so that's the number of x squareds I've got. What about the x's? I've got minus 6 here, and I've got 10kx's here, so can I write that like this? I've written the 10k before the minus 6 just because it looks a bit nicer than minus 6 plus 10k, but I could have done it the other way around. And then, what about the numbers? Well, don't forget I want this to be a 0, so I'm going to take away 25 from both sides, which will get rid of that, so actually I'm just left with plus 9. Now, this is a discriminant question, so we know that A is the number of x squareds, B is the number of x's, and C is the constant term. And the discriminant, b squared minus 4ac, remember we're told we've got two solutions, two distinct points. So I know that for two solutions this is going to be greater than 0. So I'm going to substitute this into this and see what I get. You pause and have a go at that as well. Okay, so b squared, I gridded it out. That gave me 100k squared minus 120k plus 36. And then I've got minus 4 times a times c. Well, I did minus 4 times c, minus 4 times 9 to give me minus 36 times a, which I then multiplied out. Make sure you didn't lose the minus there. Simplified it all, got this. At that point, you could have just solved it using your quadratic solver. C is 0, there's no constant term, and got the solutions that way. 0 and 15 over 8, 1.875. Or you might have decided, no, I'm going to solve it properly. Now remember, what we're doing here is, when we solve this, is working out when it equals 0. And we know that this is a quadratic, so it will be, and it's a happy quadratic, so it'll be this shape. So it equals 0 when k is 0 and when k is 15 over 8. Now we're not actually interested in when it equals 0, we want to know when it's greater than 0. So where is this graph above the axis? Well, it's above the axis before k is 0, so when k is less than 0, and after k is 15 over 8. So it's a tails rather than a sandwich. Now that's, it's interesting, isn't it? That question, you needed to spot that you were going to use the discriminant. Now, how did I know that that was a discriminant question? And actually, if you look in the mark scheme, there's a few other ways of doing it. But it's just experience, isn't it? And this is why plugging through these papers it's so valuable, because there's no way I can teach you every possible way things can be asked. But if you've done 10, 15 practice papers, by the time you set the real thing, well, happy days. Okay, I'm not going to do 15 because actually we've done that one before. But always very happy to answer any emails you have about other questions from that. And I promise that will be my last video for this year. Take care.